In this ICFD++ tutorial, we are going to demonstrate the steps to set up and model an axisymmetric jet engine intake using the new integral Computational Multiphysics Advanced User Interface, or ICMP AUI. In this example, we will introduce the user to three different boundary conditions that may be used to model an engine inlet: a Mach number specification, a mass flow rate specification, and a pressure imposition. Before starting the example, I will briefly cover the new features and components of the ICFD++ AUI for our first-time users. For a more in-depth understanding of the ICMP AUI features that are common across all Metacomp software, you can click on the ICMP AUI demo link that will show up at the side of this video, or by referring to the ICMP AUI section of your ICFD++ documentation. The ICFD++ interface is composed of 5 items. The menu bar at the top, where my mouse is currently hovering, allows you to access various tools, load and save your input file, etc. The toolbar below this, which has shortcuts to some commonly used functions and controls. The canvas, here where the geometry or solution can be displayed. And the notebook, which currently shows ICFD++ setup steps, and finally the action panel on the left-hand side where much of the problem setup takes place. Within the notebook panel, ICFD++ shows an action tree or setup wizard which can guide you step by step through the various parts of the problem setup. There are also one or more information trees. In this case, we see the groups and boundary families tree and the boundary conditions tree. Each item in the action tree or information tree has corresponding items that show up in the action panel. This is where the user is given specific choices about the problem setup based on information supplied in previous panels. All panels are dockable and resizable so the user can customize the interface. Next, I'll briefly cover the mouse controls. The mouse is used to control the view of the geometry in the mesh within the canvas. Holding down the left mouse button and moving the mouse up and down, or left and right, will rotate the geometry about its horizontal or vertical axes. Holding down the middle mouse button and moving the mouse up, down, left, or right allows you to translate the geometry up, down, left, or right. Holding down the right mouse button and moving the mouse left or right will rotate the geometry about the axis normal to the screen. And holding down the right mouse button and moving the mouse up or down will zoom the view in or out. Next, I will open up a new AUI and start the case setup from scratch. Upon launching CFD++, the user interface will open and we will see the first item in the action panel. The first panel prompts us to choose a working directory. In Linux, the default directory location is where you launch the user interface. Next, I will press OK to select the current working directory. At this point, we can select Yes to both analyze our grid files and also read the BC family file. Press OK. After loading the grid files into the AUI, information about the cell types, the number of cells, the number of cell groups, and the number and name of the BC selectors is displayed. Here we can press OK. Focusing our attention back to the left side of the screen, we see that the next item in the action tree is the Cell Types and Volumes panel. This panel is automatically populated according to how the mesh files were interpreted. The user typically will not need to change these settings. So we can press OK. Next, we see the General Problem Definition action panel. Here we will solve a compressible, viscous, turbulent, single-phase, single-species, non-reacting flow problem. This falls into the category of a general fluids problem. We will choose No for using a problem setup wizard and press OK. Next, we see the CFD Problem Definition panel. Here we choose the following options. Under Fluid Type, we choose gas. The species content, we'll choose a single species. For the question, is the flow compressible, we'll select yes. For the type of gas, we'll choose perfect gas. For the flow speed, we'll choose mostly below Mach 0.5. The next two options ask us if the flow is viscous and turbulent. For these options, we'll select yes. We'll select no for additional flow physics. And for the nature of the simulation, we'll choose steady state. And press OK. Next, we see the panel where additional specifications can be included. We will choose no to all of these options and press OK. Next, we see the equation properties panel. First, we are prompted to select between the pressure-based solver and the density-based solver with preconditioning. Here, we will choose the preconditioning option. We will also choose the two-equation realizable k-epsilon turbulence model. Select no to define passive scalars, and press OK. Next, we see the physics source terms panel. This panel allows us to introduce various types of source term effects. We will choose no to these options and press OK. Next, we see the reference quantities panel. Here we will elect to solve the case in dimensional mode using the International System of Units. So we'll choose SI and dimensional and press OK. Next, we see the fluid properties panel. Press the Edit button in this panel to specify the fluid type. We will see that air is the default species type. Here we could have chosen any of the species in the list. We will choose air, press OK, and accept the default properties for air by pressing OK. Next, we will define a base pressure level of 1 atmosphere. So we'll enter 101,325 for the base pressure level. We can keep the buoyancy terms turned off. Under the advanced settings, we'll keep all of these set to no, and we'll press OK. At this point, we will see the initial conditions action tree panel. Here we will want to choose the option to initialize the entire domain. Other initialization options are available, such as initialization by boxes, cylinders, or cell groups. We will choose temperature-based initialization because we'll specify an initial temperature in our domain. We will need to press the green plus button to add the initial condition information set. And the following values will be used. We can set the initial pressure to 0. This is relative to the 1 atmosphere base pressure. We can set the static pressure to 288 Kelvin. We can set the x component of velocity to 68 meters per second and keep the y and z components of velocity set to 0. We will wait to initialize the turbulence quantities. In this panel, we can press OK. At this point, we will see the boundary conditions action tree panel. So we can zoom in and take a look at our geometry. In the groups and boundary families information tree, we can highlight the names of the different boundaries. In this case, the inflow is the main inflow. We have a far field boundary and we have an outflow boundary. We also have a symmetry boundary. Down below, we can see the walls of the engine. And finally, the engine inlet. In this case, the engine inlet is actually an outlet boundary from our domain. This is where we'll specify different boundary condition types in this example. The BCs named inflow, far field, outflow, symmetry, and inlet will all be set to open BC types. The BC named walls will be set to a type wall. So we can start by dragging the BC named inflow to the open category. Under the boundary conditions subgroup, choose inflow and outflow. We will also choose permittive variables for the type of information to be specified. We would choose characteristics based under the condition to be applied. Here we will reuse the information set already defined for the initial conditions. So we can highlight that information set, select it, and double check those conditions, and press OK. You'll notice that the inflow boundary under the Groups and Boundary Families information tree now has a green check mark indicating that we've assigned boundary conditions to that BC. Next, we can drag the BC named far field and drop this into the same category as the inflow BC. This BC will now be assigned the same properties as the inflow. Next, we can drag the BC named outflow to the open category. At the top of this panel, we can choose outflow only. We will select the option to impose a BC at this boundary. We will choose pressure for the information type option. For the pressure type, choose back pressure imposition. Here we will need to create a new information set by pressing the green plus sign. We can highlight that and enter 0 for the back pressure. We can keep the characteristics-based option and leave the remaining portion of the panel and press OK. Next, drag the BC named symmetry to the symmetry category. Here we will choose the basic symmetry option and press OK. Next, drag the BC named walls to the wall category. Here we will choose viscous, wall function, adiabatic, and stationary with respect to mesh motion. You can leave the remaining options unchecked and press OK. Next, drag the BC named inlet to the open category. In this case, we'll be defining the engine inlet boundary conditions, which are actually an outflow from this domain. So in this case, we'll choose outflow only for the boundary condition subgroup. Again, make sure to impose a condition at this boundary by checking this box. We will choose pressure for the information type option. In this example, we will be demonstrating a few different boundary conditions for the engine inlet boundary. In this example, we will demonstrate a few different options for this boundary. First, we'll demonstrate the use of a back pressure imposition. We'll also use the option to adjust the back pressure to match a defined mass flow rate, and we'll also use the option to adjust the back pressure to match a defined Mach number. First, we'll set up the mass flow rate option. In this case, we'll press the green plus button to create a new information set. We'll highlight that information set and enter the following values. For desired mass flow rate, we'll enter 180 kilograms per second. We'll have a starting pressure of 0. This is once again relative to the base pressure. We can set lower bounds for this pressure at this boundary, minus 20,000 pascals and plus 20,000 pascals. And then we can keep the same relaxation values as well as the step number for the pressure adjustment and then the step increment for the pressure adjustment, and we can press OK. Next, we will set up the engine inlet boundary condition as if we were going to impose a Mach number at that boundary. So we can highlight that information set and press the Edit button. Again, choose the pressure for the information type option. We'll keep the outflow setting and make sure that the box to impose the boundary condition is specified. Here we'll highlight the option to adjust the back pressure to match the imposed Mach number. You can press the green plus button to add an information set. We can highlight this information set and enter the following values. For the desired Mach number, we can enter 0.485. For the starting pressure, we can enter 0. Once again, enter the lower and upper bounds for pressure, minus 20,000 plus 20,000. And keep the relaxation factor and the step adjustment settings the same. And press OK. Finally, we will set up the engine inlet boundary condition by imposing a back pressure. Once again, highlight that information set and press the Edit button. In this case, for the pressure type, we'll choose back pressure imposition. And we can enter a value here of minus 12,800. We can keep the pressure imposition set to characteristics based, and in this case we'll use pressure ramping. We'll have to add a new information set to define the pressure ramping. We can highlight that information set and specify a starting pressure value of 0, a starting step number of 1, and an ending step number of 1000. This will ramp the pressure starting at a value of 0 to the back pressure of minus 12,800 over 100 steps. And here we can press OK. At this point, we've set up 3 different boundary conditions for our engine inlet, and we can now select which of these 3 will apply. First, I'll apply the back pressure adjustment to match the defined mass flow rate. So we can highlight that option, double check the values, and press OK. You'll notice in the information tree, all of the boundaries have a green check next to them, and you can drag your cursor over each one of these to see the summary of the boundary conditions that are specified. And this completes our boundary condition setup. Finally, we can press OK. Next, we will see the turbulence control action tree panel. Here we can accept all the default settings by pressing OK. Next, we will see the turbulence initialization action tree panel. Here we will need to select the only information set. This corresponds to the initial condition in the main inflow BC. We can right-click this information set to open the panel. We can choose Yes at the top of this panel to indicate that we know the turbulence length scale. We can keep the None option set, since we won't use suggestions for turbulence levels. We can enter a free stream turbulence level of 0.02. We can enter a turbulence length scale of 0.03 meters. And we can keep the default velocity setting of 68 meters per second. And here we can press the Compute button, press OK to accept those values, and press OK again. This completes the setup of our turbulence initialization. Next, we will see a panel prompting us to choose if we want help setting up the numerics options. We can select Yes here. The engine inlet Mach number is about 0.6, so here we can select the subsonic option. We can also click the plus button to show the details about the different flow regimes. Below this, we see that CFD++ asks us whether we need assistance. We can choose the Ream solver panel and the time integration panel. We can specify a flow type as external. We can enter a mean system velocity of 68 meters per second and press OK. Next, we will see the Ream Solver panel. We can accept all the defaults here by pressing OK. Next, we will see the Simulation Strategy panel. We will choose No for a restart. We will choose Implicit Integration. We will set the case to run for 2,000 steps. We can keep the order of magnitude convergence set to 5, and we can press OK. Next, we will see the time integration panel. We can keep the max CFL and CFL ramping schedule that's recommended by the Help Set Numerics wizard, and we can accept the other settings in this panel by pressing OK. Next, we will see the spatial discretization panel. We want to make sure we are running in second order mode. We will want to change the dimensionality of the polynomial to 2D axisymmetric. You can take a look at the advanced controls here. In axisymmetric cases such as this, axis stability enhancement can help, so we'll enable that and press OK. Next, we will see the neutral plot file options panel. We can select any variables we wish to report: total pressure, total temperature, velocity, magnitude. And press OK. We will need to press OK again to write the neutral plot options file, and also to copy the neutral plot options to the plotting options that will be used to generate other types of plotting variable output. So we can press OK, and press OK once again. Here we can accept the defaults for the probe and output options panel. Finally, we can press OK to save our input file. We can also choose to run the CFD++ simulation. We'll run in double precision mode. We'll run on a single CPU. At the bottom of this panel, we'll press OK. You'll notice that files are being written to the working directory. For more information about post-processing and visualization, you can refer to the results section of this example. Thank you.